with 0. So, okay, let's do this like we are doing it with our hands. Maybe it's going to be clear. The way we are reading it now, it may not make sense to some of us. So let me start.
Sorry, Mr. Fong.
Okay.
You know, why I'm asking this question because they said in Z4 and Z5 we define addition and multiplication. So at the point where we added 3 to 1, we got 0. So I'm thinking, are we dealing with Z4 or
Okay,
we are
thank
dealing
you.
with
Yes, you
Z5?
see this first one you are looking at here. Both this side addition of Z4. This one is multiplication of Z4. Z5 is below.
Okay,
Look at
it
Z5
makes
here.
more sense
Okay, I think I get the point
because
now.
as from what I'm saying here, immediately we get a value equal to 4, it reverts to 0.
Yes. The logic they are using here is that of modular operation in mathematics. Under modular operation, if you are dealing with a particular module, let's say module 5, the highest number you can get on module 5 is 4, which is the module number minus 1. So if you are dealing with module 4
Okay.
now, the highest number that will appear, whether you are multiplying in module 4 or you are adding in module 4 or you are subtracting in module 4, the highest number that will appear in module 4 is 3. But module 4 can contain up to 4 digits. 0 will be the fourth one. So look at what we are doing here. We've done addition of this first and second row. Then when we go to 1, we find out that 1 plus 3 will definitely give us what? 4,
Will give
right?
us 4.
4. But
Yes.
4 cannot appear in module 4, so we have 0. Let's move on. You see that you see some things now that will look more logical. This is 2 now. Let's go to 2. 2 plus 1. Sorry, no, we are dealing with this and this. Sorry. 2 plus 0 is 2, right?
Yes.
That is how they got this 2. Now, 2 plus 1 is 3, right? That is how they got this 3. Now, 2 plus 2 is 4. Remember that 4 will be what? 0. But look at this. 2 plus 3 is now more than 4, which is the module that we're dealing with. So this is how you now do. You revert it back to 1. Let me do something. I think this is better done showing us practically. Okay, so let me argue that I hear now. People are having issue with our network tonight. Unfortunately for me, my own network is sound tonight. The day their own network will be sound, mine will be doing like kwashoko. Okay. Once you're able to see my whiteboard, let me know. We'll drop the recording for them so that they'll watch it. Once you're able to see I'm sharing my whiteboard already. If you're able to see, let me know.
I can see.
Okay, now look at what we're saying. We are dealing with Z4. And the highest number we can get here, or let's just write out the digits. We have 0, 1, 2, and 3. This is Z4. Now, but you know that in vector space, you can do addition and you can do multiplication, right?
Yes.
So if this is Z4, 0, 1, 2, 3, I know that my 0 represents 4. Which means if I have a number greater than 4, I will start from 1 again. So if I have 5 here, my 5 will be 1. For instance, if I have counted 1, 2, 3, this is 4 now. If in module 4, I'm dealing with operation of, let's say, addition, and my addition extends to like 5, I will start from 1 again. That is
okay,
logic.
not 0.
No. 0 is already presented 4. So I will start from 1 again.
Okay, so you count 0 and
look at
you
it
count
now.
like 0.
This is now 4, 1, 2, 3. The next one that follow this one is 5. The next two that will follow it is 6. The next three that follow it is 7. That is how we do. And when you get 8 again, it's still 0. Hope you get it.
I get it.
So 9. Now we are counting in group of 4. You see that this is first set of 4. So this one now, the next thing that will follow this one is supposed to be 8, right? But it will be 0 again. That is 8. So if I still have 9 again now, now the next one will be 9, right? I will have 1 again. I will start from 1 again, which means the maximum width I can get in module 4 or in space 4 is 4 digits. I will only start repetition of that 4 digits if I have higher figures appearing in the space 4. So that is the logic. So let's go back to that their multiplication and addition and try to get what is being communicated here. We'll finish it and know I will get the idea that they're trying to show us there. So now we have 2 multiplied by 2. We have 4. That gives us 0. Then 2 sorry, we are doing addition here, not multiplication. So we have 2 plus 3 will give us 5. So we are starting from 1 again because we've gotten to our maximum number, which is 0. So we'll start from 1 again. So 5 will become 1. Now 3 plus 0 is still 3. 3 plus 1 is 4.
0.
4 in module 4 or in space 4 is 0. So 3 plus 2 is 5. We'll start from 1 again. 3 plus 3 is 6. We'll continue, which is 2.
Which is 2. Yes, makes sense.
That is the logic. Now let's go to the multiplication aspect. 0 times 0 will give us 0. 0 times 1, anything multiplied by 0, all will give us 0. Let's go to 1. 1 times 0 will still give us 0. And 0 in this case means what? 5. Don't forget. Because sorry. We are still dealing with module 4. Sorry. We mean 4. We mean 4. Yes. Now 1 times 1 is 1. So this one is clear. 1 times 2, 2. 1 times 3, 3. Now 2 times 0, 0. 2 times 1, 2. 2 times 2 is 4, which will give us 0 in module 4.
0, yes.
Or in space 4, rather. We're dealing with spaces here, not module. In space 4. Now let's move on. 2 multiplied by 3 is 6. It will give us 2. Don't forget, once you get to 4, you start from 1 again. Now 3 times 0, 0. 3 times 1, 3. 3 times 2 is 6, right?
Yeah.
Which is 2. Don't forget, when we're writing it there, we said that once you get to 0, you start from 1, 2, 3 again. So 3 times 2 is 6. And 0 is 4. Then we'll start from 1 again, which is 5. Then 2 will be 6. Then this last one, 3 times 3 is 9. Don't forget that I said that every multiple of 4 will be 0. So we have 2 multiples of 4 in what? In 8. When we count 0 to 4, 1 to 4, we have 1 0. 4 to 8, we have another 0. So we're starting from 1 again. So 9 will be 1.
Is very clear. So, that thing you explained has made these two things easy to understand. That thing you drew the 0, 1, 2 and write the values under. It has explained this whole thing. It's like they both work under the same principle, either multiplication or addition.
Yeah, so it's the same. So even this one, we don't need to waste much time. It's the same thing. Once you get to a value that is 5, you turn it to 0. Then you start from 1 again, 1 to 4. So in this one now, multiples of 5 will be 0. So when I get to 10, 10 becomes 0 again. Then I start from 1 again, 1 to 4. If I'm multiplying and I get to 15, 15 will become 0 again. Every multiple of 5 will be 0 under space 5. Then you start from 1 again. So if I should multiply or add now and I got 17, I know that 15 is 0. I don't even need to do calculation if I already know the principle. I know that multiple of 5 under space 5 is 0. So, and I start counting after that 0. I will start counting 1. So if they ask me what is 17 under space 5 without calculating, I already know it's 2. That is the idea. I already know that this is 2 because multiples of 5 in space 5 is 0. So, and I'm starting from 1 after that. So then we see that the element of both Z4 and Z5 can be added, subtracted, and then multiplied. But any operation, we carry out on them must fall within their space. So you cannot write 9 as in 9 like this, the figure, inside space 5. Where is it going to appear? That is what they're trying to say. No matter what you multiply, what you get, just know that any number outside the space cannot appear within the space. So, thus, Z4 and Z5 indeed behave like a field. So in this model, F will represent a field. So a field is like any vector that satisfies the space rule or the rule of spaces, which says that no figure, no matter the operation you carry out on the vector, none of the result must fall outside the space. So any vector that satisfies that rule, we call them field. Let's go back to the definition of the field. Under the example, or sorry, under the definition, they say division is also allowed by a non-zero element, which means when you want to divide, you know, we have been doing addition and multiplication. They say division is also allowed in vector spaces, but it's by a non-zero, which of course you cannot do division by zero now. It's infinite or undefined. So if you want to divide, it must start from one, or not. One is not even, maybe two, but not by a zero number. Then such sets in mathematics are called field. How did they arrive at the definition of field? It started from here. The real and complex numbers have the property that any pair of elements can be added, subtracted, or multiplied. Division is also allowed by a non-zero element. In mathematics, we call that field. So once you can carry out all of these operations, either on real numbers or on complex number, and they fall within the space we are dealing with, we call them field. So anyone that not fall within the space, we will learn what we call those ones later on. Examples of fields are the set of complex numbers, the set of real numbers, the set of rational numbers, and even the finite set of binary numbers, that is 0 and 1. When they say something is finite, it's countable. Binary number, we only have 0 and 1 in binary numbers. So now, you should note this place is very important in case you see it in the exam. You know that what they're asking is field. Examples of dash are the set of complex numbers, the set of real numbers, the set of rational numbers, and even the finite set of binary numbers. Examples of fields. Okay. Let's move on to definitions. The definition 1.3. Now they're giving us an official definition of a field. A field. Now, a field is an algebraic system consisting of a non-empty set F equipped with two binary operations, which is addition and multiplication, satisfying the condition. There are conditions that makes a space a space. It means any operation, the condition is that any operation carried out on a space must not give you a number outside the space. So a field is now an algebraic system consisting of a non-empty set, which means when we do the operation, the set we get cannot be empty set, which means it
must have values.
There must be values inside. So, and then we'll label it F. Then it is equipped with two binary operations. Of course, from what we've done so far, we know that the operations we do are addition and subtraction. Now,
multiplication.
Yes, sorry, multiplication rather. And we should just try to bear this in mind in case you see it. A dash is an algebraic system consisting of a non-empty set F equipped with two binary operations, addition and multiplication, satisfying the conditions, a field. If now, they say recall from Math 103, let's leave that. We're not recalling anything here. Now, vector addition. We are now going to another thing. Vector addition. Let me see. Do we still have time? Because I really don't want us to rush anything. Although this course is like we have to rush because the material is very long. But
This thing, commutative law, associative, we did it last semester.
Yeah, sure. Now this one is just basic math. So in vector addition, to every pair, the u, the v, and is a subset of r raised to power of 3. To every pair, u, v, being a subset of real numbers, that capital letter R is actually real numbers, there corresponds a unique element, u plus v is a subset of the real numbers. You already know what I'm calling subset to. This or belongs to or subset. So let's call the addition of vectors such that u plus v is equal to v plus u. That means they are commutative. When the position does not matter, they are commutative. Of course, we know that addition is commutative now because when you add 4 plus 2, you will get 6. If you still add 2 plus 4, you still get what? 6.
Plus 6, yes.
Then we have associative. U plus v plus w is equal to u plus into bracket of v plus
V
w.
plus W. Associative.
That is associative law. In the real sense, let's replace them with figures and see if that law really works. I know we already know this. It's not even something we should be wasting time on, but let's just try and do something. Because his assumption has been what is killing us all this while. You assume some people know, and we've forgotten that most of us left school a long time ago. Even basic math, some people don't even know again. So let's see what we can do on this notepad. I don't want to start sharing dashboard again. That one is taking us too far. So we are trying to confirm the associative law. Assuming those symbols are to be replaced with, let's say 2 plus 3, that is our u is 2, our v is 3, and our w is, let's say 5. You know that this will give us what? In the real sense.
That's 10.
What to do with bracket first now? 5 plus 5, 10, right?
Yes.
According to board math. But you also know that the second part says that is the same thing as saying now u plus into bracket of v plus w, and that one now our u is what? 2 plus into bracket of 3
Plus 5.
Is this still going to give us 10? We do with bracket first, right? 3 plus 5, 8. 8 plus 2, 10. Sorry. So
yes.
the law is correct.
Yes, correct.
Law is correct. So associative law is correct. Now, in real numbers, r raised to power of 3 has a unique element denoted by 0 called the 0 vector that satisfies that u plus 0 is equals to u. Of course, we know now. You know what they are trying to explain here is what we've done already in that example of addition and multiplication of Z4 and 5.
Yes, assuming
When we add anything
numbers
to 0 there, you see that we got that same thing back.
Yes, correct, correct.
Now, for every u being a member or belonging to the real numbers, called the additive identity. So that is what this law satisfies, additive identity. Now, for each of these laws, we have to get a way to master. Although you see these first two, we know them already. Let's just assume this time around we assume because we did this in math 103 or so. So we should know additive, commutative, associative. We should know all those ones by now as general things in math. So now for every u belonging to the set of real numbers, there is an element w belonging to the set of real number also that satisfies that u plus w is equal to 0. Don't forget that 0 is the 0 vector. Anybody that joined now, without being a part of our addition and multiplication of Z4 and 5, we will find some things hard to grab. So our advice, we go and watch that part later. Now, scalar multiplication. For each, now all these ones are still formulas. We've not started main thing itself. We've done addition above. Now we're going to multiplication. Don't forget that addition is for vector. Your multiplication is your scalar. That is the scalar part of. Let's go back a bit to vector space. We say it is dealing with two operations, right? A space that is with two operations, addition and what? Multiplication. Why the multiplication is for the scalar part? You know, for vector, right from the beginning of this class, we say it has both scalar quantity and dimension. So for the scalar part, the operation we do on the scalar part is multiplication. So let's go to that's why they say scalar multiplication. They do not just say multiplication of vector. Now for each u belongs to the set of real numbers, that's r raised to the power of 3. Real numbers in the real sense is just r. I don't know why they add that their own raised to the power of 3, but in any case. And is this alpha belongs to r, that is set of real number. That corresponds a unique element. Alpha multiplied by u, they both belongs to the set. You know, see, this is what we've done under Z4 and Z5 above. When you multiply 3 by 3 times 3, the number we wrote there, did we write 9?
No.
Because 9 is outside the space. So we wrote 1.
Yes.
Now that is it. So alpha multiplied by u, which is a member of the real numbers that we're dealing with, will give us a number that belongs to the real number. Can't be outside the real number. Now, this one we'll call it the scalar multiplication, such that alpha dot beta, that dot means multiplication. Alpha multiplied by beta multiplied by u will give us alpha multiplied by beta multiplied by u. That is using bracket. It's just like the commutative, is that associative law for addition?
That's yes.
Yes, it is similar to it.
Associative.
For every alpha, beta belonging to the real number and u belonging to the real number raised to the power of 3. I think this one is talking about space. This 3 that they are putting on it should be, I think it signifies space, because we are dealing with vector space and not just vector. Now, 1 multiplied by u is equal to u. That one is certain. Anything multiplied by 1 is equal to that.
It's straightforward rule.
For every u belonging to the vector space, that is the R space, where 1 belongs to 1R. Imagine all these basic things. That means this math 212 will be sweet, by God's grace. Now, distributive laws relating to vector addition with scalar multiplication. Now, distributive, we kind of want to combine the two of them together now. For any alpha, beta, which belongs to the set of real numbers, and u, comma v, belongs to the set of the real number space, the following distributive laws hold. Alpha multiplied by, we said that distributive law is going to combine the two of them together. Which two of them are we talking about?
Addition
and multiplication. Thank you. So for alpha multiplied by u plus v will give us the same thing as alpha multiplied by u plus alpha multiplied. You know this one now, expanding of bracket.
Very straightforward. Algebra.
Yes, thank you. Thank you.
Algebra.
Okay, we have a full house now. Sorry, I don't know you guys have joined back. Welcome. So the same thing will that be? Do we have to, please, who don't understand all those things? So all this u plus v plus alpha plus beta that you're saying. If you don't understand, let's stop this assumption that we believe we all know it, so that we'll treat it to. Although we've done justice enough on that. Now, for the above properties to hold for any collection of vectors, we have the following definitions. It's even sweet that this course is full of definitions, because if it's calculation, it is well. a vector space V over F, denoted by V of F, or in short, V, if the field F is clear from the context, is a non-empty set. They've mentioned this before, in which vector addition, scalar multiplication can be defined. They are just modifying the definition they've given above. This is the same thing we have been working by. We gave a very simple one to ourselves the other time, that the vector space is a space of vector that has two operations, addition and multiplication. And we said that the multiplication deals with what? Scalar quantities. That is what they've just rephrased here. But for the sake of exam, please try to know that once you start seeing a dash V over F, denoted by V of F, or V if F, or if the field F is clear from the context, is a non-empty set in which vector addition, scalar multiplication can be defined. You should know that what they're asking you is vector space. Please, once you are reading the material and you see anything bolding like this, try to read that place over and over again until you, whether you are cramming it or something, let it sink. Those ones are almost likely to come out every year in the exam. Anything you see, you see that they don't bold in much. But I'm not talking of titles like this. So, as in within the context, something is bolding. Always pay attention to those things. That is exactly how they will cut it out in the exam. Now, in other words, a vector space is composed of three objects: a set and two operations, addition and multiplication. Further, with these definitions, the properties of vector addition, scalar multiplication, and distributive laws, see items 1, 2, and 3 above, we've done that, are satisfied. Now we have remarks. I hope you are not rushing though. We are rushing because we felt this part is sweet to go. Now, the definitions that have been given above, the properties of vector addition, scalar multiplication, and distributive laws are satisfied. Okay, yes. Now for the remarks, A, the elements of F are called scalars. Where did you notice that they mention F in the definition of what? Vector space. V over what? F. You know that V is a vector, which is the addition. The F is the one that will do scalar multiplication on. So that's why they say that.
Yes.
V if F is clearly defined in the context. Oh, sorry, I hope I'm not jumping. So that is A. Now, for B, the element of V are called vectors. Of course, we know already. Because when we say V of F, and we know that we have two operations in vector space, the addition and multiplication. Multiplication is for the scalar, which is the F. V are the vectors. So now, the zero element of F is denoted by 0. We know that one. Whereas the zero element of V is also denoted by 0. I think Anderson will relate to this. When we are doing multiplication under Z4 and 5, you notice that the zero element on both multiplication and addition remains 0. So when I add under Z4, when we added 2 plus 2, we wrote 0. Under multiplication, when we multiply 2 by 2, I will go 4. Under the Z4 space, we also wrote 0. So it doesn't change in the 2. In fact, it seems once you are able to digest what we did under that Z4 and 5, every other explanation they gave below that level is just referring back to what has been done on that Z4 and 5. Note that the condition 1D above implies that for every U belonging to V, which is vector, U being a vector, the vector W belongs to V, such that U plus W is equal to 0, holds, is unique. This is a bit, but it's straightforward too. But it will be better if you use numbers to understand what they're trying to say. If U belongs to a vector, the vector W belonging to V, such that the addition of the two of them is equal to 0 volts. If the two of them is equal to 0, that means they give you the space you are working under. If you are working on space 4, and W plus U will give you 0, then under space 4, W and U and W are either 1 and 3 or 2 and 2. I hope you understand what I'm saying. For you
Sorry,
to
please
get
run through it
0
one more
under
time.
any space, then the two things you added or you multiply, they are giving you that same space you are working under. That is how you
Yes,
got
yes,
0.
yes. Yeah.
That is what they are
It
trying to
will
do.
give you, yeah,
So
I
for
agree.
instance, if you are
Like
working
for
on
that
space 5,
Z4,
if you are, I think we
for
are working
Z4,
on space 5, this U and W can only represent two things, 1 and 5 or 2 and 3, because those are the two things that will give us 5 under addition. You understand? But under multiplication, only 1 and 5. But here we're dealing with addition. So in this case, two things can give us okay, under addition, 1 and 4 and 2 and 3. So it's either you will take this, we will assume the space of 2 and W3, or U3, W2, or they are 1 and 4, or switch them anyhow. Okay. If W1, W2 belongs to a vector with U plus W1 or WIN1 is equal to 0, for I is equal to 1, 2, then by commutativity of vector addition, can you recall the law of the commutative law? We've treated it above. We see that
U
W1,
plus W is equals to W plus U.
so we see that W is equal to W1 plus 0, which is equal to W1 plus U plus W2, which is equal to W1 plus U plus W2. It's just the same thing. I think we treated that with this itself, example here, something like that. So that it's going to be clear to us. So all these commutative, distributive, whatever, just know them by default, like know them by heart. They are basic things in mathematics. Every other thing they're saying here is just drama. And try to grab, thank God I recorded that part. So those of you that missed it because of network or you were not there, then watch it. The part when we're treating Z4 and 5, we've done justice to that. Hence, we represent this unique vector by minus U and call it the additive inverse. Okay, I think we got a new thing here. When you get subtraction, when your answer is having a subtraction, a minus is on the negative line, you're having additive inverse under commutativity or under commutative law. If you add in the result here, let's say what we add together here is giving us minus 10 or minus whatever. We are doing additive inverse. Now, if V is a vector space over R, then V is called a real vector space. And if V is a vector space over C, then V, which is a vector space, is called a complex vector space. We know R and C now. From the beginning of this unit itself, they talk about real numbers, R, complex number, C. So those ones, it's just like, I think this is summary of the whole thing itself. All these remarks is like their summary. In general,
Summary of what we have.
yeah, what we've done before. In general, a vector space over R or C is called a linear space. Let's not forget. That was when Mr. Valentine was trying to explain linear space the other time. Or linear, is it linear space or linear equation, whatever. Or linear vector, or linear space. But we said we should leave that to another class. Or sorry, as an homework, everybody should go and work on it. For better understanding of the conditions given above, the following theorem and proof are presented, but we will not go into that tonight. Please, we have just 4 minutes left, and we're not starting any class again because I don't even have light on my system anymore. So far so good. We've treated vector space right from the beginning. We gave definitions on several levels. We even gave layman definitions. We gave example of somebody cooking rice and beans. We gave that of a club, the Infotech Club, for our understanding. And we've treated Z4 and Z5, which is space 4, space 5, and we did addition and multiplication. And the whole idea is that vector space, vector on its own, deals with two things. It's two operations going on. But vector space is also dealing with two operations, which is the addition of vectors and multiplication, which is the scalar part of it.
Scalar.
Yes. So I think that is the root thing. Once you grab that one, then you know that what you are doing. Then when we got to space in full, we said that when you are multiplying or adding under a space, your result, whatsoever you get, must not be outside that space. I will not repeat Z4 and Z5. Go and watch it. You will understand it. I will drop it very soon after the class before my system goes off. So is there any question? Any addition? Thank you so much. I think
So far,
it's a
I'm good for
wonderful
now.
class.
I'm good.
All right. So is there another person still here? If we don't
Yes,
have question, if we don't have
OBI.
contribution, let's call it a night or a day. Thanks for attending. Seriously, this class, I myself have gained a lot from it. I think I'm prepared. Anything they will set under this part now in the exam, let them bring it. I'm ready. So,
Mr. Sam.
thank you. Have a wonderful night rest. See you
All
on
right.
Monday. No class tomorrow. We'll meet on Monday for the next course. We are following our timetable serially. That's what we are doing. If you notice, we started with which one is that? That first course that we have on December 1. Then we'll follow it to the next one, GS303. Then we'll move to March 212. Anything we have next in line is what we'll do on Monday. That's how we'll be doing it repetitively until exam time. Have a wonderful night, rather.
All right. Thank you, Mr. Sam. Good
You're
night.
welcome.